Welcome to Chapter 13, Introduction to Landforms. We are finally going to talk about the solid part of the Earth, the lithosphere. With the lithosphere, we are able to talk about how mountains and valleys form, ocean basins, the floor of the ocean, and earthquakes and volcanoes. In fact, in this picture here, you see lava from Mount Kilauea. And this kind of lava is actually very smooth in terms of how slow it erupts from the volcano. And if it ever actually erupts in Hawaii near, let's say, houses and property, an average person could actually run from it. I went to a different volcano. This is this is Mauna Loa on the Big Island of Hawaii, where Mount Kilauea in the last slide was also on the Big Island of Hawaii. And I traveled about 10,000 feet in sea level. And this is what the top of the mountain looks like, or close to the top of the mountain, in the summertime in Hawaii, where just an hour ago, I would have been down in Hilo, Hawaii, where it was sunny and very lush and green. So this is me standing near Mount Kilauea. In July, a couple of years ago, it wasn't erupting, but there was still steam coming off of the volcano. This was taken actually from a caldera in Iceland. And this, I think I mentioned in the first set of lecture slides, this was used as an amphitheater for an Icelandic pop singer, Bjork. It's such a cool place to not just hear a concert, but to see some of the amazing geologic aspects of Iceland, basically an island filled with volcanoes. The most common terms for Chapter 13, we will be looking at a concept called uniformitarianism, then a little bit about geologic time, the pieces of the inner parts of the Earth, the solid parts of the Earth, the crust, mantle, inner core, and outer core. Talk about which one of those produces the magnetic field. There are three basic types of rock: igneous, sedimentary, metamorphic. Then the large theory, and really it's a really well-agreed law behind the way crust pieces move around the Earth, is all in within plate tectonics. If you're following along in the book, you might realize that we don't really get into plate tectonics until chapter 14. But I like to talk about it in chapter 13 to set the stage of the sort of the cycle that we see when we have plates moving around and them causing earthquakes and volcanoes. And then we'll also talk about something called a hot spot. Uniformitarianism. So the largely agreed upon theory in geology, especially when we think about going back in time, is that the present is key to the past. So the processes that have shaped the land in the past are still shaping the land now and will shape the land in the future. So given that, we can look at vast periods of time where certain geologic processes had operated. However, instead of doing that, and instead of actually memorizing all of these periods of time, to give you an idea of this geologic time scale, I have posted on Canvas a geologic time scale PDF, and it shows you when things have happened, as if we took all of the Earth's time and spread it out over one calendar year. So based on geologic time, the Earth has been around for about 4.5 billion years. So if we squeeze that whole time into one calendar year, humans actually have only been around since December 31st at 11:48 p.m. So given that the Earth started on January 1st, that means that if the entire Earth was only 1 year old, then humans would have been around for only 7 minutes. So that's something to think about. Right, I said 11:48, so actually that's 12 minutes, but still, that's quite a short amount of time compared to the entire Earth. So the processes that shape the land that we see and the oceans, we are going to focus on the internal processes. That's what chapters 13 and 14 do. They look at the internal processes that shape the land. So that means we need to talk about the structure of the Earth. The part of the Earth which we all live on is called the crust. And the crust is a very thin layer of the Earth. It's about 5 kilometers below the ocean, but nearly 20 kilometers below the land. So a question for you is, why do you think the crust below the ocean, which we call oceanic crust, is thinner than the crust below air, basically? The reason is density. The ocean compresses the crust to the point where it's very dense. It's also very thin, whereas continental crust isn't as dense, and so it expands more, and it's not as dense. It's not as it's actually a lot thicker. Another interesting thing is that the crust only constitutes 1% of the Earth's volume and only 0.4% of the Earth's mass. But it's a pivotal piece because without the crust, we would not have life that we know it on Earth. Below the crust is the mantle. This is typically semi-solid, and it encompasses the largest of the 4 pieces of the Earth, 84% of the total volume and 2/3 of the total mass of the Earth. And it can go down to about 1,800 miles. Now, the interactions between the mantle and the crust pave the way for our explanation of plate tectonics, which is the focus of chapters 13 and 14. But we still want to go farther into the Earth. The outer core is actually molten and extends to about 5,000 kilometers. The magnetic shield, which actually protects life on Earth and produces the aurora borealis and the aurora australis, the northern lights, is produced by the outer core because of the certain elements that are in the outer core, iron and so forth, and radioactive material in addition to that will set up a huge magnetic, sometimes we call it field, sometimes we call it shield, that helps keep many of the sun's harmful radiation out of the lower atmosphere. So if we didn't have a molten, moving around outer core, we would not have life on Earth. Now the inner core, by the time you get way down near the center of the Earth, you have such immense pressure. And at this point, we have mainly iron and nickel. The temperatures of these are so hot that if they were at sea level, they would boil away. But the pressure is so great that it only allows these elements, these minerals, these materials, to be solid. And so that makes an extremely dense mass. In fact, 15% of the Earth's volume is the inner core, but 1/3 of the entire Earth's mass is the inner core. So here's a blown up version of your 4 biggest internal pieces of the Earth. And what I want to point out is that the interaction between the continental crust and the upper mantle, which is sometimes called the asthenosphere, is where we can get a lot of action in terms of earthquakes and volcanoes. Some students often ask me, well, how do we know that these are down in, these are the layers within the Earth? Because we can't necessarily go down in there. The answer is seismic waves. So we have seismometers set up around the world. And when any kind of earthquake occurs, especially large ones, they send out pulses and waves across the Earth, and they go through the center of the Earth. When they do that, they may switch direction as you go from, let's say, the mantle here, and then once they are in the liquid outer core, The densities are different between the two, and so we have something called refraction, and the earthquake waves change, and they change direction. And so based off of that kind of data, we have a good idea of what is down there and how deep these layers are. So we're going to go back up to the crust for a little bit and talk about rocks. Rocks are composed of many different minerals, but about 95% of all of the rocks have fewer than 20 minerals. And with rocks come certain types of rocks called outcrops. I like to talk about outcrops a little bit because in and around the San Fernando Valley, especially if you're driving from the San Fernando Valley to Simi Valley, you might see a lot of rocks, seemingly random, along that pass between the San Fernando Valley and Simi Valley. Those are rock outcrops, and they're outcrops because they were at one time much further down into the surface of the Earth. But because of tectonic activity, earthquake activity, they have eventually made their way up to the top of the Earth, and now they're called outcrop. The part of the Earth where we see a much more stabilized rock formation is the bedrock. You may have gone through the types of rocks when you took a science class either in grade school or high school. So we're going to go through this a little bit here as well, but eventually what I want to do is I want to get into something called the rock cycle. So to start off with this rock cycle, let's talk about igneous rocks. Igneous rocks, igneous actually, means fiery inception, and they come directly from volcanoes. Magma is basically liquid rock that is beneath the surface, but we call it lava when it's on top of the surface. So when lava becomes rock or when magma becomes rock, we have igneous rock. So because of those two things, we have two types of igneous rock. Plutonic or intrusive are the ones that basically form from magma beneath the Earth's surface. And a very common type is granite. The type of rock that you might see forming directly from lava on the surface is basalt, and we call that volcanic rock. If you've ever been to the Hawaiian Islands, there is so much basalt all across the islands, and that's because of pretty active volcanic activity, especially on the Big Island of Hawaii. Eventually, if we maintain this sort of cycle, eventually these igneous rocks will break down. And they can break down by disintegrating through processes that are related to water, to air, to wind, and even ice at sometimes. And eventually, what happens is a large amount of sediment will form in one location, and if it sits there for a long enough time and has enough pressure, it'll start to create a new type of rock, sedimentary rock. And again, this requires an enormous amount of pressure to sort of lock in the particles of the sediments. So right here, we're looking at a very cool feature from Utah. This is in southern Utah. We have a dramatic example of sedimentary rock. Now at the bottom of my circle I've drawn here, you see layers of sedimentary rock, and they're mostly horizontal. Those are, it's like cutting through a new rock. Those are very classic shapes and layering that sedimentary rocks can have. Now above, we have a little bit of a different look because of wind erosion and maybe a little bit of rain. The farther you go down into these rocks, the older the rocks will be. That's one other general uniform law that we have in geology, unless something disrupts this layering like an earthquake. But eventually these sedimentary rocks will form, and you'll have so much pressure, and these rocks will start to go beneath the Earth's surface, closer to the mantle where it gets warmer. And if that's the case, oh, by the way, yeah, here's another picture of a really cool looking sedimentary rock with very cool layered features. This is also near Utah, but I actually believe this is in Arizona. It's the same kind of rock we just saw in the last one, except this time it was, um, this was where people were actually walking on it. So it's quite immense and amazing in terms of the picturesque aspect of this, this hike that a person can take. Sedimentary rock, very cool geologic features that would form this. But eventually these rocks have so much pressure, and because they're getting below the Earth's surface and closer to the mantle, so much heat that they become metamorphic rock. So igneous can become uh, metamorphic. Sedimentary can become metamorphic, actually. But we're staying in a cycle here, so we're going to just go from sedimentary to metamorphic. You can think of metamorphic as cooking of rocks. And what happens is you start to get wavy patterns in these rocks. And it's a chemical change also to these rocks. So limestone can become marble. Shale can become slate. And some of the coolest rock features that that you might see extruding to the surface of the earth are metamorphic, because it's not just layers like sedimentary, but we have wavy patterns in different colors. Eventually, though, oh, by the way, this is another sort of cut through a large piece of rock, and you can kind of see the really interesting wavy patterns. So eventually, once we had igneous rock, then we had sedimentary rock, then we had metamorphic rock. Eventually, those rocks get heated up so much that they melt and they can become magma. And magma can actually extrude from the volcano once again and create igneous rock. So after the rock cycle, what I want to talk about now is a much larger process that we see with the Earth's crust. Obviously, rocks go through a certain cycle, and what we have on Earth, the solid part of the Earth, is basically fixed. So that's why we have a lot of different recycling processes. Plate tectonics is one large recycling machine. And what it does is it moves the continental crust around. We see seafloor spreading. So we see down the middle of large basins, large pieces of oceans, the seafloor actually spreading apart. And when the seafloor spreads apart, it produces new crust. At the same time, we have subduction, which forces crust to go down back into the surface of the Earth, beneath the surface of the Earth. And those two processes, seafloor spreading and subduction, are the largest pieces that drive plate tectonics. You may have heard of Pangaea. So Pangaea is thought to be the last supercontinent that we've had, and we're right now in the process of the breakup of Pangaea. Eventually, going into the future, we will see another supercontinent. The boundaries or the dividing areas between these plates is what creates problems on the surface of the Earth. That's where we find most of our earthquake and volcanic activity. So once again, we're going to talk about plate tectonics, but we're going to divide it up into two pieces. This part right here is the overview process of seafloor spreading. So you might be asking, well, why does the seafloor actually spread? The theory is we have pieces of magma that are hotter than magma nearby, and they rise through convection, just like when we were talking about convection and air parcels rising in chapter 6. When they rise, they hit the crust and they spread outward, and it drags the oceanic crust along with it. So magma, once it gets onto the top of the surface of the crust, its lava starts to form, and they create volcanoes along large ridges of ocean areas. Now, this crust has to go somewhere. It's being pushed. Eventually, it gets, for some reason or another, different densities. Usually, it's different densities. A piece of this will start to dive underneath continental crust because oceanic crust is so much more dense than continental crust. Even though we don't see a large area of subduction right here on the eastern coast of South America, we see a major subduction zone along the west coast of South America. And in fact, that's one of the biggest reasons why we see large earthquakes, the Andes Mountains, and large volcanic eruptions along the west coast of South America. Because of this process, we can actually develop a relative age of the oceanic crust. Areas where we see new crust forming, which would be near seafloor spreading centers, are the youngest rocks. So you see some very young rock, young being, 0 to 2 million years old. And then areas where we see subduction, and one particular subduction area that is very prominent because it creates the largest, or I should say the deepest part of the ocean, is the Mariana Trench. The deepest ocean spot that we know of is about 7 miles deep, and it's due to the subduction zones. So old rock we find near subduction zones. New rock we typically find near seafloor spreading areas. So even though Iceland is land and not ocean, it's actually part of the large mid-Atlantic ridge. So the mid-Atlantic ridge is a very large seafloor spreading center that goes up and down the middle of the Atlantic Ocean and is actually responsible for splitting or tearing apart the island of Iceland. So in this picture, what you're seeing is a bridge that's connecting the part of Iceland that's on the North American plate and the part of Iceland that's on the Eurasian plate. Kind of cool, especially for a geographer or a geologist. So this is another term that we use for plate tectonics. You might see it as continental drift. And Pangaea isn't the only one that we know of. About 500 million years ago, we started to we know of another supercontinent. In fact, I believe there are 3 or 4 supercontinents that geologists have labeled within Earth's 4.6 billion years. 225 million years ago is when all the continents were put together. And if you think about it, even today, South America kind of looks like it used to fit with Africa. That was the first piece of evidence that led scientists about 100 some years ago to think that the continents were moving around. So this is over here approximately what the continents looked like 65 million years. And then of course down below is what they look like today. Now, those are the process behind pieces of crust, which are called plates moving around. The boundaries of these plates, again, is where we find earthquakes and volcanoes. What this is showing you are different boundaries and how they're moving. If you have convergent boundaries, that means pieces of crust are being pushed together. And so what we see here, especially along the west coast of South America, is a major convergent boundary. Divergent boundaries are where plates are moving apart. And areas that move parallel to each other, like the San Andreas Fault, we call those transform boundaries. We're going to talk more about this in chapter 14, especially in relation to earthquakes and volcanoes. So if you take a look at a map, you You show the plates and their boundaries. Then you add on the volcanoes, the volcanic areas, which are in these small triangles, and the earthquake zones. You see a pattern. You see that most of this activity, most of the earthquake and volcanic activity, are along plate boundaries. And that's because that's really where the Earth is moving. The Earth and its crust are moving around due to the processes of the mantle, due to convection. And so we'll get into the details of earthquakes in the next chapter, but you can imagine when big pieces of crust and its rocks are moving around, it'll rattle the Earth. And will also allow for seepage of magma through volcanoes. Now there's one type of volcano. You see these orange circles in the ocean that are not due to plate boundaries, and they're called hotspots. Hotspots are due to not magma seeping through plate boundaries, but deep-seated plumes of magma. And these plumes of magma, they don't move really that much in a long amount of time. However, the crust on top of it moves much quicker, much more at a faster pace. So a good example of this are the Hawaiian volcanoes. Over here in Kauai, this island used to be over where the magma plume is, but it has moved northwest. Oahu had also used to be there, and then as you see these series of islands, it just so happens today that the big island is the spot that is over the magma plume, so it has the most active volcanoes. A new big island will be forming and is already forming now, and will eventually be located where the big island is today. So a hotspot is responsible for the island chain of Hawaii. There are other hotspots around the world, and one of the most well-known and closer to home is Yellowstone. And so in the next chapter, we will get into a little bit more detail of what happens at these plate boundaries and how earthquakes and volcanoes can result from these pieces of crust that break at certain locations.